The urgency behind this billion-dollar comeback is revealed in the construction of the most powerful machine ever made, a metal monster designed to dominate deep space through brute force and precision. The secret to this haste lies in technological superiority and the need to validate the Space Launch System, or simply SLS. This 98-meter-tall giant is modern engineering's answer to overcoming the limits of low Earth orbit. Its core stage, manufactured by Boeing, rises 65 meters and houses 4 RS-25 engines, the same ones that propelled the old space shuttles, but now optimized for a one-way journey. With 2 massive tanks that store millions of liters of liquid hydrogen and oxygen, the SLS is not just a means of transport, it is a declaration that the infrastructure for a permanent presence is ready. Unlike any previous project, the SLS uses solid fuel boosters that provide most of the thrust in the first few minutes of flight. In 2026, these boosters will bear a unique detail, the commemorative logo for the 250th anniversary of the United States, symbolizing that this effort involves engineers from every American state. It is the embodiment of an industrial power seeking to regain leadership in space, using familiar components but integrated into a completely new and radically more powerful architecture. To understand how this brute force translates into survival, we need to look to the top of this fire tower, where the Orion capsule protects the mission's most valuable resource. Orion is the technological jewel of this project, composed of 3 fundamental sections that guarantee the safety of the crew. At the top, the crew module provides the pressurized environment where the 4 astronauts live and work. Just below, the European service module, provided by ESA, acts as the life support and orbital propulsion system, supplying electricity, water, and oxygen. Without this international collaboration, Orion would be just a drifting metal shell. It's a technical symbiosis where each solar panel and each maneuvering thruster must operate in absolute harmony with the American navigation systems. Many question the astronomical cost of this hardware, but NASA's central argument is that only this extreme redundancy allows it to safely navigate the vacuum of space. The heat shield at the base of the capsule is designed to withstand atmospheric re-entry at speeds never before tested by modern manned spacecraft. We are talking about a flying laboratory that tests the limits of materials science and human biology simultaneously, serving as the first real step in transforming the neighboring satellite into a launch pad for the rest of the solar system. The efficiency of this hardware is tested to the limit when the main engines stop roaring and orbital physics takes complete control of the crew's fate. A recurring question among enthusiasts is how the rocket manages to put the spacecraft on the exact path to the moon without missing by a single kilometer. The secret lies in the upper stage, known as the Interim Cryogenic Propulsion Stage, or ICPS. It is this stage that performs the Translunar Injection maneuver, a precise burn that alters the Earth's orbit to a lunar intersection trajectory. If this ignition lasts 1 second less, Orion will never reach the satellite's gravity. If it lasts 1 second longer, the astronauts could be launched into the infinite void of the solar system. This surgical precision is what allows the mission to exploit what we call the SEO DNA of space exploration: safety, efficiency, and objectivity. The trajectory was designed so that the spacecraft uses Earth's own gravity to gain speed before the final jump. During this initial phase in high Earth orbit, the crew performs proximity tests and manual docking operations, ensuring that the hardware responds instantly to the commands of pilots Reed Wiseman and Victor Glover. It's an orbital dance where error is not an option, and every kilogram of fuel is accounted for. Consider the paradox of carrying millions of liters of explosive fuel just to keep 4 people alive in a space smaller than an average SUV for 10 days. The contrast between the monumental scale of the SLS and the cramped space of the Orion's cabin is shocking. While the rocket consumes tons of propellant per second during liftoff, astronauts Christina Koch and Jeremy Hansen must manage every milliliter of drinking water and every gram of CO2 filtered by the life support systems. There is no luxury, only the raw functionality of survival. The air recycling system must be flawless, as any failure in removing toxic gases would result in a silent catastrophe long before the spacecraft even gets close to the moon. This delicate balance between the raw power of the launch and the fragility of human life in space is what defines the true risk of Artemis II. The SLS structure has been criticized for being based on decades-old technology, but NASA argues that the reliability of the RS-25 engines is the only guarantee that the necessary thrust will be delivered without catastrophic failures. The development cost exceeded billions precisely because every bolt was tested to withstand vibrations that would disintegrate any terrestrial structure. The challenge is not only to get there, but to prove that this disposable rocket architecture is still the safest way to take humans beyond the protection of Earth's magnetic field. The hardware seems invincible, and the flight plan is mathematically perfect, but there is a critical flaw that engineers try to hide in the fine print of safety manuals. During the translunar injection phase, the Orion capsule becomes vulnerable to a phenomenon that no onboard computer can predict with complete accuracy. If a micrometeorite strikes the heat shield or service module during this critical burn, the crew may not discover the damage until it is too late to return. The mission's success depends on a statistical gamble against the hostile environment of deep space, where the smallest particle can become a destructive projectile. Understanding this vulnerability leads us to question whether the mission design prioritizes science or mere political survival in a race against time. The deliverables of this phase of the project are clear. The SLS and Orion function as an unparalleled power unit, designed to overcome the vacuum. The success of the Translunar Injection maneuver will prove that humanity has regained the ability to navigate between worlds. The integration of long-range communication systems ensures that, even hundreds of thousands of kilometers away, the crew's voices reach control centers clearly. This is the thesis of Artemis 2. Current technology has not only equaled the Apollo era, but surpassed it in terms of automation and structural resilience. If you want to understand how each of these technical components could fail or save astronauts' lives in the coming days, subscribe to the channel now. Turn on notifications to receive an alert as soon as we reveal the hidden dangers that NASA prefers not to detail in its official broadcasts. Space exploration is made up of details that go unnoticed by most. Here, we delve into transcript data and actual flight plans to reveal the truth behind the epic images. Do you believe the billion-dollar investment in the SLS is worthwhile, or should we have opted for more modern, reusable rocket technologies? Leave your opinion in the comments to fuel the debate about the future of our species beyond Earth. Orion is now traveling at escape velocity, leaving the safety of Earth behind and heading towards the pale glow of our satellite. The four explorers watch the planet shrink through the window as the darkness of deep space becomes their only companion. The hardware delivered on its promise, but the journey is only beginning. From now on, life support is the only wall between them and certain death, and every heartbeat of the ship is monitored by thousands of people on the ground. Trust in the machine is total, but human nature is unpredictable under constant pressure. But while the thesis of technological perfection is celebrated, a disturbing contradiction arises. If the rocket is so powerful and the spacecraft so safe, why are the radiation data collected on Artemis 1 causing chills among the mission's doctors? There are levels of exposure that could compromise the crew's health long before they complete their 10-day flight. What the sensors detected in the previous unmanned mission suggests that deep space is far more aggressive than mathematical models predicted. In the next stage, we will confront this grim reality and discover why this journey may, in fact, be a dangerous one for which the human body is not yet fully prepared.